this is David Van Vranken here at UC Irvine. Welcome to our sixth lecture in the Chemistry 51C series, the third quarter of organic chemistry. And we're starting on what is arguably the most important chapter today in the entire year-long course, and that's the chemistry of carbonyl compounds. And in the next lecture, and within this chapter, we're starting to talk about a class of reagents that are called pyrophoric reagents that are so unbelievably reactive that they burst into flames when they come into contact with air. These are incredibly dangerous reagents to work with, but also incredibly powerful reagents for bond-forming reactions, and that's what makes them so interesting. I'm starting off with a picture of a chemist squirting some of these reagents out of a syringe, a solution of one of these pyrophoric reagents. We usually use syringes and syringe needles to transfer air-sensitive reagents in the laboratory. It's a standard technique that we use. Let's go ahead and take a look at a video for how these reactions work. So here's a video that I pulled off the web. I think most chemists, myself included, have done this before. And you can see what happens is you squirt these reagents. Wow, look at that. It just bursts into flames. Of course, our fume hoods are lined with flame-proof walls. You would never do that if there's equipment sitting in there. So let's take a look at what happens as these droplets fly through the air, as this liquid flies through the air, this solution. He was working with a solution of tert-butyllithium. It's got a carbon-lithium bond in pentane. This is probably the most reactive and most pyrophoric reagent that we work with in my laboratory and many laboratories. And it just happens to be sold as a solution in pentane, which is one of the most volatile and most flammable solvents that we work with in the laboratory. So what a dangerous combination. And I'm showing you in these boxed pictures kind of what's going on at the interface between the liquid and the gas phases. So in the liquid phase, we have pentane and tert-butyllithium, and in the gas phase up here in yellow, I've depicted water and oxygen molecules. There's other inert gases there, but I haven't drawn those. And the reaction that is so incredibly exothermic is the deprotonation of water molecules by this alkylithium compound. That carbon-lithium bond is so nucleophilic and so basic, it immediately grabs a proton from any water molecules that it comes in contact with. And that is so exothermic. It generates so much heat. And I've depicted the heat with these delta symbols, but really heat is the motion of molecules vibrating, moving, colliding more frequently. And that heat is enhanced because there's a second reaction, the formation of a very favorable oxygen-lithium bond. And so with these higher temperatures and more frequent collisions and faster molecular motions, reactions that don't occur at room temperature start to occur, such as the reaction of alkane molecules with molecular oxygen that leads to combustion. The solvent ignites and bursts into flames, and if it's like gasoline and any other flame or any flammable solvent, that's what's catching fire there. Okay, so that's the class of reagents we're going to introduce in this chapter. Incredibly interesting. Keep your eyes open for reagents that have this much chemical reactivity in them. Let's go ahead and get into chapter 20. This chapter is about addition of nucleophiles to carbonyl groups. And let me go ahead and start off by trying to contrast what we're doing in this chapter and what we're doing in this quarter of organic chemistry with all the stuff that you've done in the past. In this chapter, we're going to be learning about reactions of carbonyl compounds and the nucleophilic addition of molecules to carbonyl compounds, like this ketone right here. So the main theme of this chapter is we're going to take nucleophiles. Sometimes those nucleophiles will have reactive lone pairs. Sometimes those nucleophiles will have immensely reactive bonds that attack things. And throughout this chapter, what we're going to see over and over again is this pattern where nucleophiles will attack carbonyl carbons, and then you will push the electrons up to the carbonyl. You have to get used to this reaction. This is so fundamentally important for modern organic chemistry, for modern organic synthesis, for biology, for biochemistry. This is really the way organic chemistry works. The way to understand this reaction is that there's another resonance structure we can draw for for ketones, for aldehydes, for esters, for amides, an incredibly important resonance structure in which we put the electrons from the bond, we push those electrons up to the oxygen. Oxygen's electronegative, so it should enjoy having that negative charge. The electrons from that double bond, maybe they want to spend more time on the oxygen. And when we redraw a carbonyl compound using this resonance depiction, the second best resonance depiction doesn't have as many bonds, and it's true that the carbon doesn't satisfy the octet rule, but at least it explains why so many nucleophiles love to attack carbonyls and allow the electrons to get pushed up to the oxygen. So get ready to see this process over and over and over again. Mechanistically, we refer to this as addition. We refer to this as nucleophilic addition, and nucleophilic addition to carbonyls is the most common. So depicting, if you draw the resonance structure where you depict this carbonyl in this form as an oxido-substituted carbenium ion would be the lingo. Drawing this as a carbocation will help you to understand the reactivity of carbonyls. There's about 25% of a positive charge on a typical ketone, like acetone or methylethyl ketone, as I've drawn it here. And so this is such a powerful way to make carbon-carbon bonds. You can expect for me to ask you questions about this. You'll see questions about this in every single organic chemistry class by every single instructor. Get used to that pattern of reactivity. And I want to contrast this super important aspect of reactivity with all of the stuff that you've seen before. Everything that you've seen before seems like it has been so heavily geared toward a completely different class, a less useful class, a less common class of reactions, and that's SN2. So far, you've been trained to look for leaving groups, electronegative leaving groups like bromide, tosylate, chloride, protonated water molecules, and then take nucleophiles and try to add them in to those substrates for SN2 reactions. And there were so many limitations to this. You had competing E2 eliminations, or if you had a capacity to generate carbocations, then you had to worry about whether it would go through an SN1 or an E1 mechanism. Steric hindrance would slow these reactions down. And so on a secondary alkyl halide substrate like this, the likelihood is you get just a lot of competing E2 elimination. And so it didn't work very well, or it was so sluggish. And so these types of processes were just not very good, but that's all you had available to you. It's the only reaction that you had available to you. And so they worked this reaction in the textbook, so overworked it in a really tiring way that you're going to have to fight your tendency. You will have a tendency to overuse this reaction for everything. So SN2 reactions are just not very good. Why did we spend so much time training you on something that doesn't work very well? Not sure, but let's get on to something that does work well, and that's addition to carbonyls. Now, throughout this course, this third quarter of organic chemistry, we're going to talk about two patterns of reactivity with respect to carbonyl compounds. And it depends on what's attached to those carbonyl compounds. So what you look for on your carbonyl compound is, does it have a leaving group? So in the case of this acid chloride or acyl chloride, in the case of esters, in the case of other types of substituted carbonyl compounds that have potential leaving groups, we're going to find that those undergo substitution reactions. So let's see how these types of substitution reactions work. It's a two-step mechanism. It's always a two-step mechanism. It's never a one-step substitution of the leaving group. Somehow or another, I think because SN2 is the only, and SN1 were the only process that you saw, you might be thinking that there's always some one-step process, but that's not true. These reactions start off with an addition process, just like I showed you on the previous slide here, where the nucleophile attacks the carbonyl. That's certainly going to happen, and we refer to that as addition. So again, what I'm looking for in this case, case is the presence of a leaving group. Let me just note that that was there. That doesn't affect the fact that this starts off with an addition step. So we'll get an intermediate that has 4 bonds to carbon. Let's go ahead and draw those 4 bonds in. And one of those substituents on that carbon atom is going to be this incredibly nucleophilic alkoxide species there. And there's my leaving group. Look at that leaving group. Now, somehow or another, you learned all kinds of rules about leaving groups for SN2 reactions. You can't have hydroxide act as a leaving group. You can't have alkoxides act as leaving groups. Those are only true for SN2 reactions. If you put an alkoxy group or a hydroxy group or a chloride group next to directly next to an oxido like this, no problem pushing that out. You can't stop that from getting pushed out. You couldn't isolate this species if you wanted to. That reaction of pushing out a leaving group, methoxide, hydroxide, is so fast. Chloride, bromide, you couldn't stop this from getting pushed out. You can't isolate this kind of intermediate. It would immediately push out the leaving group. So that process of pushing out the leaving group, we refer to as a mechanistic elimination step. So I'll just write elimination. This process of addition and elimination of a leaving group is going to be super important coming up in a couple of chapters. And so I want you to be looking for these cases where we have leaving groups. And in fact, they're going to bring it up in this chapter, even before you're really ready. Oh, I love carbonyl pi bonds. They're so stable, right? That's what makes carbon dioxide stable. So much of organic chemistry is driven by the formation of CO pi bonds. There's just such an amazing driving force for formation of CO pi bonds. So within chapter 20, we're going to see some of these processes where we push out a leaving group. Alkoxy leaving groups will be very common. But the main theme for chapter 20 is just carbonyl compounds in general, aldehydes, ketones, that when we take powerful nucleophiles like alkyl lithium reagents, or one of these reagents that you've seen before, sodium acetylide anions, these will add to carbonyls. This is way better than any kind of SN2 reaction. Nobody really uses sodium acetylide reagents for doing SN2 reactions. People make them so that they can add them to carbonyls. That's the way the first birth control medicine was made, was synthesized, and it's still common in the synthesis of pharmaceuticals. So when you add powerful carbon nucleophiles to ketones and aldehydes, you'll get these new tetrahedral centers in most cases, right? If you wanted, and it would be very painful, you could go through the trouble of trying to isolate this sodium alkoxide, but really, no chemist ever wants to isolate a salt. We want to isolate, which is water soluble, we want to isolate organic soluble molecules. And the reason why we want to isolate molecules that dissolve in organic solvents is we can easily evaporate the solvent. Water doesn't evaporate easily. Organic solvents evaporate so easily. So really, pretty much in every single case in this chapter and going forward, when we add a nucleophile to a carbonyl and end up with a stable product with no leaving groups on here, right? There's none of these groups can leave. We protonate this with a workup. And I'm usually going to write not just H2O. I usually, even though the book doesn't like to do that, like to write the word workup, so you know that when I'm adding water, I'm not trying to hydrate this alkyne. I'm not trying to do SN1 or SN2 reactions with the water. I just want to protonate some O- so that I can get a neutral molecule and that can be extracted into an organic solvent. So you'll have to draw these. I'll show you reaction after reaction involving organometallic reagents, carbon sodium, carbon lithium, carbon magnesium reagents, where we follow these up with a second step in order to protonate the alkoxide product, because nobody isolates these as negatively charged alkoxides. We isolate them as neutral alcohols that can be easily purified, easily dissolved, and extracted in organic solvents. So this is the theme we're going to see in chapter 20, add to carbonyls. Look for leaving groups, potential leaving groups when you add to carbonyls, and you're going to have to get used to the idea that hydroxide and alkoxides can act as leaving groups when there's a carbanion or an alkoxide directly next door. So that's going to be a struggle to overcome these crazy rules that you learned for SN2 reactions and repurpose and generate a new set of rules. Let's talk about our first set of reagents. that are incredibly powerful. Not powerful enough that they work for SN2 reactions, but incredibly powerful. I'm going to introduce you to two reagents that have nucleophilic bonds to hydrogen. And you've never seen these reagents before. I'm not sure if you've learned about the process of oxymercuration reduction reactions. You might have seen one of these reagents before, but not in used in a useful way for generating carbon-hydrogen bonds. Here's the first reagent. Let's go ahead and get started. It's a third row atom. Let me go ahead and just sketch out a little bit of the periodic table here. Boron, carbon, nitrogen, oxygen, fluorine. That's the second row of the periodic table. But right below that second row is a third row with larger atoms. Aluminum, silicon, phosphorus. These are bigger atoms. They have longer bonds. Let's draw some of those bonds. I'll draw them freakishly long. Well, the hydrogen's not bigger. I shouldn't have drawn that bigger. Long bonds are reactive. Long bonds are more nucleophilic. If it's to a leaving group, then it makes the leaving group leave faster. So this is our first reactive species. It's called tetrahydridoaluminate, and you usually buy it as the lithium salt, often called lithium aluminum hydride. The other common reagent that we're going to see that's a hydrido delivery reagent is borohydride. It's got 4 bonds to boron. It's got a negative charge. And this is sold as the sodium salt. So sodium borohydride and lithium aluminum hydride. Sometimes I circle my charges if I think you won't be able to notice that they're there. These are the common forms you buy these reagents. But forget the lithium or the sodium. Those are not important for your understanding of how these reagents work. The important thing is that these are 8 complexes. This is called an aluminate with 4 bonds. With a negative charge to aluminum, I refer to that as an aluminate. This is tetrahydridoaluminate. And when I hear the word aluminate, I know there's a negative charge, and I know that every lone pair and bond on that aluminum atom is nucleophilic. That's why it's important to call it an aluminate. And when I refer to this one down over here as a hydridoborate, borate tells me there's a negative charge on boron, and every lone pair, there's no lone pairs on these, or every bond to that atom is nucleophilic. I know the bonds to this boron atom are going to be nucleophilic because it's a borate species. So I pay attention to those suffixes on here. And these bonds are nucleophilic. What are they going to attack? Of course, they're going to attack carbonyl groups. So let's go ahead and get started on using these bonds to hydrogen as nucleophiles so we can transfer these hydrido groups to carbon atoms. Those bonds are super nucleophilic, and you're not used to seeing nucleophilic bonds. But in this chapter, you're going to see a bunch of nucleophilic bonds like those carbon-lithium bonds that burst into flames and they get exposed to air. These reagents are not equally reactive. Tetrahydridoaluminate is vastly more reactive than tetrahydridoborate. It's considered a pyrophoric reagent. So it's a third row atom, and those long bonds to the aluminum make those bonds super reactive. Tetrahydridoborate, still reactive enough for carbonyl chemistry, but I'm not sure if that's saying much. It's so easy to add to carbonyls. It's so easy. Oh, I love it. We're finally here in chapter 20 to talk about the real meat of organic chemistry, which is addition to carbonyls. Let's go ahead and start off with what's really a problem that's kind of related to that tert-butyllithium bursting into flames, is that we have to watch out for the presence of water and OH bonds. If you want to use reagents like tetrahydridoaluminate reagents, here's one of the things we have to worry about. We have to worry about alcohols being around. We have to worry about water molecules being around. Do not use tetrahydridoaluminate if you have OH bonds anywhere in your reaction mixture. Or even, you can't even have your flask exposed to the air, because long before this will attack any carbonyl compound, these bonds in the tetrahydridoaluminate will much more quickly deprotonate OH bonds on carboxylic acids, on water, on alcohols. This is so fast, so unbelievably fast, you cannot stop this process from occurring. So, and if you've taken the time to buy this reagent and prepare it to put into your reaction, I promise you, you weren't using this reaction to deprotonate alcohols. We have easier reagents for doing that, like sodium hydride is one that you've already learned about. So this is an unwanted side reaction, always. Nobody ever wants to do this. So you have to watch out for this. Here's my arrow pushing tells me I'm going to, according to this arrow pushing, I'm going to generate hydrogen gas. If you add these reagents fast enough, you'll generate so much heat that the hydrogen will burst into flames. I'll just write flames here. So if it gets too hot, the hydrogen gas ignites and you'll start a fire. So don't ever expose tetrahydroaluminates to any solution or any gas phase that contains water vapor or water molecules. If you go through the trouble of excluding air, wet air, air always contains moisture in it. If you go through the trouble of excluding air, water, OH bonds from your reaction mixture, and I should not just say H2O, I should say ROH, or carboxylic acid. If you exclude those things rigorously and run your reactions under dry nitrogen gas, which is what we do, now we can start to look at some interesting patterns of reactivity with tetrahydroaluminate and tetrahydroborate. And here's the interesting reaction that occurs is we'll take those nucleophilic bonds to the aluminum atom like this. Oh my gosh, those bonds are so nucleophilic. And we're going to push those electrons into the carbonyl. And of course, we kick the electrons over to the carbonyl oxygen. Now, the frustration I think that many students feel when they enter this chapter, when they enter the third quarter of organic chemistry, is you can't tell from my arrow here whether I'm going to form a bond between aluminum or hydrogen. You can't tell. The arrow pushing doesn't tell you that. You know one of these things will end up attached to the carbonyl, and then the reader has to wait until, but if we attach the aluminum to the carbonyl carbon, we'll still have a negative charge, and we want to give a product that gets rid of that negative charge. So it's the hydrido group, the hydrogen that ends up attached to the carbonyl carbon. And as soon as I draw it, you know what I meant. You'll see which product I intended after I draw the product, but you couldn't really know that before. So there is another potential outcome based on my arrow pushing, but nobody would make an aluminum minus bonded to carbon on purpose. That wouldn't actually be probably not a favorable process, but you do want to generate carbon-hydrogen bonds like this. And the leftover reagent is this very weird species called alane, kind of like borane, BH3. And boy, I kind of feel like I want to make a bond between O- and aluminum. Aluminum loves oxygen, being bonded to oxygen. Okay, so I'm telling you how powerful of a reagent this tetrahydroaluminate is, but don't use it for SN2 reactions. It's not good for SN2 reactions on alkyl iodides, on alkyl bromides, and alkyl tosylates. You could get a little bit of product if you add it to epoxides, and I think the author of our book just loves trying to do additions to epoxides, but in reality, those aren't very good reactions. Really, tetrahydroaluminate is for adding to carbonyl compounds, and that's what we're going to do with it in this chapter, in two different parts of this chapter. So let's go ahead and talk about this, these reactions of tetrahydroaluminate and tetrahydroborate with carbonyl compounds. Now, we don't want to generate alkoxide products and get stuck there. We like to go a little bit further and protonate the O- so we can have neutral compounds. And I'm going to show you how to depict these two-step sequences where we add a nucleophilic reagent like a hydroaluminate or a hydroborate, and then we follow that with a reaction of water. So if I tell you that I want to see, for example, it's oftentimes on my exams, I'll ask you what reagents or steps or sequence of steps would you use to accomplish the following transformation? Would you use to reduce this carbonyl compound down to an alcohol? And the key reaction that has occurred here is we've made a hydrogen-carbon bond. This is the challenge. At this stage of organic chemistry, I expect you, the first thing I expect you to see is that you formed a carbon-hydrogen bond. Not just that you formed an OH bond. Even though we don't draw that carbon-hydrogen bond, that's the first thing I expect you to see. So let's go and draw this two-step sequence. The book often enumerates these like this, using Arabic numerals and brackets. That's fine. I often use a lowercase Roman numeral I. I use those lowercase Roman numerals to indicate that you don't really isolate anything in between these two steps. You don't isolate and purify anything. So step one would be the lithium tetrahydroaluminate, which generates an O- product, but we need to protonate that to put an OH bond on there. And so we follow this up with an aqueous workup. And I usually write the word workup there. I'll put it in green. You don't have to write the word workup. The book doesn't write the word workup. I just want you to know when I write that in there, when I write it for you, I want you to know that we're not trying to do some SN1 or SN2 chemistry by treating this with water. It's just to protonate the OH, swamping it with a vast excess of water that, so that you do just an acid-base exchange. Now, one of the biggest mistakes that I see in organic chemistry, which will cause you to miss all the points on this question, is if you don't enumerate the steps. If you mistakenly draw it out like this, and I'm just going, before I draw anything, I'm just going to tell you this is wrong. This would be completely wrong. Lithium aluminum hydride. If you write it out like this inside the box, and water, and you don't enumerate the steps, step one, step two, that's completely wrong. I told you what happens if lithium aluminum hydride is present with water. It will react instantly with the water, generate hydrogen gas, and cause a fire. So I won't count this in any way correct. If you simply leave out those numbers, then you misunderstood the organic chemistry behind hydroaluminate, and I won't give you any points whatsoever for that. So if I draw some sort of a box and I say, tell me how to do this, you have to remember to draw 1 and 2. And that's the only way to get that correct. Okay, let's take another example, because there's another hydrido reagent that we introduce you to, and that's sodium borohydride. So if I ask you, how do you take this aldehyde and convert it to this alcohol? Again, there's 2 H's here. We just formed a new CH bond. Then you could use sodium borohydride for that as well. Let me show you another way that I typically enumerate reagents. If you don't isolate anything in between, if you're not trying to do a purification of anything in between, I often use these little Roman numeral I's. That's more common in research publications. And then you could follow this up with water. You don't have to write the word workup there. I often write the word workup. We're not trying to do SN2 or SN1 chemistry with the water. It's just there to protonate the O- product. So that's the purpose of the water. So if I ask you how to do this transformation, you could do step 1, lithium aluminum hydride, step 2, water, or you could do step 1, sodium borohydride, step 2, water. But there's one other recipe. It's kind of a secret recipe that you'll see in the sapling learning problem sets. You'll see this in other textbooks. Maybe you'll even see it here in this textbook. There's a secret reagent combination. So secret combo, I'll call it. It turns out that sodium borohydride is so much less reactive than lithium aluminum hydride. Now, lithium aluminum hydride has those long reactive hydridoaluminate bonds. Sodium borohydride is so much less reactive, you can actually run the reactions in methanol. And it will start to deprotonate the methanol, but it is so much less reactive that it can actually attack the carbonyls and give you good yields of both addition to the carbonyl and protonation of the alcohol when you simply put all of this in together at the same time. So with this very particular reagent combination, this secret combination, and I'll just write okay. It's okay to write in the box like this. You can do sodium borohydride in methanol as a solvent, and you don't have to enumerate those steps. In fact, you don't. You dissolve your ketone or your aldehyde in methanol, and this only works with ketones and aldehydes. And then you scoop in some sodium borohydride powder, and you don't need to do a second water step. But you can't do that with lithium aluminum hydride. Only sodium borohydride has that, is kind of meek enough to allow you that flexibility. You've got to be careful about the products that you're making, because we're starting off, when we talk about ketones and we talk about aldehydes, oftentimes we're talking about substrates that have only 3 groups attached to a carbon in a carbonyl carbon. And in the end, we've now added a 4th substituent. And you have to watch out for the creation of stereogenic centers. So anytime you have 4 atoms attached to a carbon atom and they're different, that's now a stereogenic center. And I ask you on my exams, clearly indicate stereochemistry, so use dashes and wedges for bonds if you need to, and the presence of stereoisomers, if any. If you also create a mirror image, you should say +E. If you create a diastereomer, you have to draw that diastereomer out. So, I'm getting more people saying that the audio quality is not good on this talk, and I don't really know how to fix that. But I promise you I'll make some sort of a duplicate recording of this if the audio quality is becoming too frustrating, and I'm sorry about that. Don't have control of the internet. I'm here on campus and it should have a much better internet than my home. So we'll see what we can do about that. Okay, so let's go ahead and talk about this idea that you have to watch out for creation of stereogenic centers. So when I take this type of substrate that has 3 different substituents and I make a 4th bond to that carbonyl carbon, let's go ahead and watch what happens here. So I take and this would also be true if I use a lithium aluminum hydride reduction. Doesn't matter which reagent I'm using. And this bond, all these bonds to boron in this tetrahydroborate are nucleophilic. And so that's going to add into the carbonyl. There we go. And it's going to create a stereogenic center. Now I get to choose. What you don't know is whether I'm adding to the bottom face of the carbonyl or am I adding the hydrido group to the top face. So we can be arbitrary about which of these we draw first, as long as we're clear that we're generating both combinations. If the hydrido group adds to the top of the carbonyl, then I'll end up having the hydrido group on top. And if the hydrido group adds to the bottom of the carbonyl, I'll end up with the hydrido group on the bottom. And you can't control that in this reaction. You're going to get a mixture of both. So you'll end up with both of these products in this reaction. So you follow these reactions up, you need some source of protonation here. So I told you there's a 2-step sequence up above here that we're doing. And so the next step in this case would be protonation of the you just swamp it with water. And if you use a big excess of water, right, then you'll end up transferring protons to this. It's really an equilibrium process, but if you've got a lot of water, Le Chatelier's principle says that most of the protons will be attached to your substrate. And so the final product will be a mixture of both enantiomers. You won't have any control. You'll get a 1-to-1 mixture of this plus the enantiomer. When I draw a box and I say draw the products in the box, you can just write +E. As long as you clearly indicate the stereochemistry, if the only product has the mirror image is the enantiomer, then you can simply write +E. When I ask you to draw arrow pushing mechanisms, and I'm interested in the arrow pushing, usually I write on the question, don't worry about stereochemistry. In most cases, when I'm asking you to draw the curved arrows for the arrow pushing, I'm usually not asking about the stereochemistry in that. And I'll tell you that. I'll tell you, don't worry about stereochemistry. Okay, so tetrahydridoborate and tetrahydridoaluminate. Super key reagents. Well, I promise you, every single section of Chemistry 51C will be asking you questions about those 2 reagents. You simply need to know that they form hydrogen-carbon bonds by adding hydrido groups to carbonyls. And so now I'm going to show you another very special reagent that is going to seem out of place. And it's a reagent that you use when you want to substitute esters. And the reagent goes by the acronym DIBAL-H. And here's the chemical structure of DIBAL-H over here in the corner. It stands for diisobutylaluminum hydride. And you don't really need to know this chemical structure of DIBAL-H. You don't need to know that it stands for diisobutylaluminum hydride. It's not a hydridoaluminate with a negative charge. They don't show you the mechanism for how this works in the book. And if they're not going to say anything about the mechanism, it's completely different from the hydridoaluminate with a negative charge. Since they don't tell you how it works, and it doesn't work like lithium aluminum hydride or tetrahydridoaluminate, then I don't expect you to know the structure for that. But what you absolutely need to know is that if you have an ester of some kind, that ester will be substituted by this species. So look at what's happening here is that if you start off with a methoxy group on here and you treat this with this two-step sequence, DIBAL-H followed by a water workup, that you'll end up substituting the methoxy group. It is not an SN2 reaction. We're not going to show you the mechanism, but I promise you it is not SN2. And whenever I draw a box and I say, tell me the products of the reactions, I want you to draw all the products that contain carbon in that box. I mean, that's what I really expect you to draw. So even though this you wouldn't actually isolate in this reaction because it's more volatile than the organic solvents we work with, I want you to show me that you can tell what happened to this fragment if it contains a carbon atom. If it's just a chloride anion, I don't care whether you show those products in the reaction. Okay, let me try to make the fanciest and most exotic substrate I can here. I'm just trying to see if I can distract you. So quite often we're going to have things that look like this, right? Maybe we'll have this here. And I've got a ring to throw you off, and I've got an ether in there to throw you off. I'll put a chlorine atom in here. I mean, you can't ever do SN2 reactions on chlorine on these types of species, but the point is that when you see all of this blizzard of functional groups and we see an ester, if you see me treating an ester with DIBAL-H, and you follow that up with a water workup, you don't have to write the word workup. I just like to do that so it's clear. I'm not trying to do SN2 reactions or some other weird thing you learned from an earlier chapter. The products of this reaction will involve substitution of the methoxy group by an H group, by a hydrido species. And so the product of this is the aldehyde, and the other product is the alcohol. And you need to know this pattern of reactivity. You need to practice problems with this pattern of reactivity. You need to practice problems with tetrahydridoaluminate. You need to practice problems with DIBAL-H, and that's just something that you need to practice with. So notice notice this pattern of reactivity. Okay, I'm going to show you a very different fate. If I come back to that other reagent that I showed you, tetrahydridoaluminate and an ester, you get a very different product out of that. If I take this cyclic compound that has an ester and I treat that with tetrahydridoaluminate, it turns out it doesn't stop at that substitution product, it keeps going. Let's go ahead and see what happens with that. All right. I've got, let's go ahead and try to draw out another substrate and imagine if instead of treating this with DIBAL-H, what would happen if we treated this product, this starting material with lithium aluminum hydride and did our two-step sequence there. So I'll do step 1, lithium aluminum hydride, and step 2, H2O workup. So what's going to happen with that? Now, this is not a ketone. I already showed you what happens with ketones and aldehydes. You add one hydrido group and you get an alcohol, and that's the end of the reaction. But in this particular process, because it's an ester, notice that this is an ester, not a ketone, not an aldehyde. With an ester, when you treat those with lithium aluminum hydride, the products of these reactions have been burned all the way down, I don't know if that's the correct term, but have been reduced all the way down to the primary alcohol. And you get another product out of that, that's the leaving group here. And that comes from the aqueous workup, protonates the O-. We'll talk about the mechanism in a second. So you need to know this pattern of reactivity. So when you've got esters, lithium aluminum hydride cleaves the pond, and reduces the carbonyl all the way down to a primary alcohol. We've added 2 hydrido groups. There were 4 on the lithium aluminum hydride, and we've added 2 of those hydrido groups. And the cis stereochemistry, the Z stereochemistry, that double bond doesn't change because we didn't make or break any bonds to that alkene. Now the book shows you one more transformation. They tell you that if you take these crazily reactive species called acyl chlorides, so you learned about acyl chlorides with Friedel-Crafts acylations. Those are going to be money reagents later in later chapters, but basically they're showing you that if you have a leaving group that's even better than a methoxide leaving group, that you'll be able to get those to be substituted as well. Maybe they're thinking that you're so used to seeing SN2 reactions of halides that that's the only thing you can grasp, but this would certainly work. I'm not going to draw the chloride, it doesn't contain any carbon atoms, but just not common. This reduction of acid chlorides or acyl chlorides, it's not useful in synthesis. No chemist on the planet Earth would ever do this. It would work if you did it, but nobody would ever do that. So can't envision I would ask you that. But maybe in sapling, in the sapling online homework, they might ask you this. I don't even know why they're teaching you that. That's not at all common, whereas this transformation above is very common. Okay, let's go ahead and see what where we're going to next on this. We've got one last thing to talk about today, and that's the mechanism. What's going on? Why does it add 2 hydrido groups? And the mechanism for this transformation is complex. This is going to be the start of us showing you mechanisms that involve 5 steps, 6 steps. Chemistry 51C involves a lot of multi-step mechanisms, and this is going to be one of the first ones that you're going to see that involves so many steps. Let's go ahead and take a look at the mechanism for that hydrido group reduction of esters by tetrahydridoaluminate. We're not going to talk about the mechanism for DiBAL-H substitution. So let me go ahead and draw out this tetrahydridoaluminate, and I'll draw just one of those 4 bonds, those very nucleophilic bonds here to that aluminate species. That bond is so nucleophilic, that long aluminum hydrido group bond to that aluminate species. And so now, after we add here, we're going to generate a bond to make this unstable tetrahedral intermediate. There, we've got a bond now to that what used to be the carbonyl carbon. And now we have this alkoxide anion. Now, I think somewhere back in Chem 51A in the first quarter of organic chemistry, you were told don't use hydroxide anions as leaving groups. You were told don't use methoxide anions as leaving groups. But that was only for SN2 substitution reactions. We're going to use hydroxide as leaving groups all the time in this quarter. We're going to use alkoxides as leaving groups all the time in this quarter. When you've got an anionic lone pair right next door to a hydroxide or an alkoxide, you can't stop that group from getting pushed out. This is not an SN2 reaction. That is going to happen faster, so fast that you couldn't possibly isolate this if you wanted to. You can't. It will instantaneously push out that leaving group. When that nucleophilic lone pair is right next door, whether it's a carbanion, a nitrogen anion, or an oxygen anion, it will immediately push out that leaving group. And it will give this aldehyde that is now more reactive than the ester that you initially started with. We'll talk more about the relative reactivity of aldehydes and esters in a later chapter, in chapter 22. But for now, just recognize that you've generated a carbonyl that I already told you reacts with lithium aluminum hydride. So let me draw another hydridoaluminate species. Could be the same one you start with or some sort of a byproduct. But as long as you have tetrahydridoaluminate in that reaction mixture, I already told you that these can react with aldehydes and ketones. And so you can't stop this from reducing again. You couldn't stop here if you wanted to. If you wanted to stop here, I told you the reagent to use. If you want to stop at the aldehyde, use DiBAL-H. That's the only way to stop here. But if you're using lithium aluminum hydride, it'll keep reducing again, and so it'll add a second hydrido group, whether you want it to or not. That's what's going to happen here. And you get this, I'm not sure we have to draw this out each time. We get this, this species is called alane. Don't worry about that. That's not the important. So this is what will be sitting there at the end of your reaction. And then finally we come along and we do our workup. I'll put that into a different color. This is step 2. So we have H2O. If you just swamp it with a bunch of H2O, you're going to transfer protons to the product. This is now the workup for this process. Let me draw one of the 3 lone pairs on there. And so now at the end of the reaction, you've come back from lunch, your reaction is complete, and you want to work up the reaction and make it neutral so you can extract it into an organic solvent and then evaporate off the solvent. And there we go. The other thing that will happen is you'll notice that this OR minus was still floating around the whole time. It was still floating around the whole time. And that's also going to protonate under the conditions of this reaction. So, you know, the next step that will happen here is that, well, I mean, it's not necessarily one faster than the other, but both of these O minus species will be protonated when you swamp this with water. You can't stop this from also getting protonated by water. So you'll also see this protonation. Let me go back to this this nice green color that I'm doing for my aqueous workup. But you'll also protonate your alcohol leaving group, whether that's a methoxy group or an ethoxy group. Those will be protonated as well. So you'll get 2 products out of this reaction. You'll get the reduction of the carbonyl to a primary alcohol, and then you'll get the leaving group in its protonated state. All right, hydrido group reagents, lithium aluminum hydride or tetrahydridoaluminate, sodium borohydride, DIBAL-H. You absolutely need to know these reagents. You need to practice transformations using them. And that's it for the start of really the most important chapter in the book.